Okay, Dr. Chitra, if you are there, if you could.
Yes, sure, sir. Sure. Okay, so next we will read message from Professor Leon Chua, who doesn't need a formal introduction to the audience of this seasonal school on intelligence on chip since his health condition is not okay. So he passed on to read out this message on his behalf. So it goes like this. Thank you all for attending this IEEE CAS seasonal school on the important and emerging topic of intelligence chip. I was looking forward to delivering the plenary talk. Unfortunately, I'm unable to present the talk in the workshop this time due to health reasons. I believe that the intelligent chip with embedded non-volatile memories can help break the scalability barriers imposed by the von Neumann architecture and enable efficient ways to implement and scale cognitive functions in machine intelligence. Needless to say, memristor devices and systems have become one of the front runners as a choice of implementing futuristic application with in-memory computing solution and deep learning. I would like to use this forum to bring your attention to the forthcoming IEEE special issue of Transaction on Circuits and System 1 regular paper on the 50th birthday of the memristors, which include several papers having high relevance to this seasonal school. I would like to draw your attention to the timely publication of a new four-volume book entitled The Chua Lectures from Memristors and Cellular Nonlinear Networks to the Edge of Chaos, which is relevant to the theme of the seasonal school. This book contains the verbatim content of a lecture series under the same title as above, which I presented at HP Palo Alto on September 8 to November 24, 2015. It consists of 12 90 minutes lectures containing mostly original concepts and theory extracted from my research and organized pedagogically via colorful slides. These 12 lectures were professionally videotaped for streaming via YouTube and can be accessed by typing the keyword Chua HP lectures in the YouTube search bar. In addition, the entire set of colorful slides from these lectures have just been published in a four-volume book by World Scientific in 2021. This timely book contains 12 chapters, where each chapter contains not only colorful slides from each lecture, but also an appendix containing many new mitten slides which had not seen the light of day. I will do my best to join the virtual school as an audience this time and look forward to hearing the talks to be presented at the seasonal school. There is a wide range of important topics delivered by a good mix of top quality scientists in the seasonal school, which should be useful for both established scientists as well as students. I wish you all to have an engaging 5 day of talks and discussion. Leon Chua. And thank you, Professor Leon Chua, for such an inspiring message. We wish you a speedy recovery and soon you'll join with us. Thank you.
Thank you, Dr. Chitra, for passing that message on. So we'll move to the next session. Dr. Alon, he has worked, I think, in the recent times a lot closely with Professor Chua, and the topic that Professor Chua was planning to present was very close to what Dr. Alon is presenting today. So I think in that sense, this can be, and it's a very important topic as well. In Memristor, those who are familiar with Memristor, they will understand it. That some of the circuit applications in the early days started with oscillator circuits and many others, which really popularized the field. So I think today, like Dr. Allen was one of the leading person who could really give us insight on this area. So I would request Dr. Chitra again to briefly introduce him, and then we'll move to the presentation.
Hi, Professor Alon Ascoli. So let me read out a brief introduction about yourself. And Professor Alon Ascoli, he received PhD degree in electronic engineering from University College Dublin in 2016. 2006. From 2006 to 9, he worked as RFIC analog engineer at CSR Sweden. From 2009 to 12, he was research assistant in the Department of Electronics and Telecommunication and Politecnico di Torino. Since 2018, he is scientific collaborator with the Department of Microelectronics, Brno University, Czech Republic. Since 2012, he is scientific collaborator in the Faculty of Electrical and Computer Engineering, uh, uh, Technical University Dresden, where he is currently pursuing a habilitation in fundamentals of electrical engineering. His research interests lie in the area of nonlinear circuits and system networks of oscillator, cellular nonlinear networks, and memristors. He was honored with the International Journal of Circuit Theory and its Application Best Paper Award in 2007. He is the president of the Cellular Nanoscale Networks and Array Computing Technical Committee since May 2019. In April 2017, he was conferred the habilitation title as Associate Professor in Electrical Circuit Theory from the Italian Ministry of Education. Since 2014, he is Management Committee Substitute for Germany in then Cost Action IZ 1401 Memristor devices, models, circuit systems, and application. He has been program chair and special session chair for the 15th International Workshop on Cellular Nanoscience, Nanoscale Networks, and their application in 2016. He is the technical program chair for the International Conference on Memristive Materials, Devices, and System 2019. And thank you, Professor Alon Ascoli, for your presentation today. And over to you, Dr. Alon Ascoli, for your talk.
Thank you very much for this nice introduction. And thanks to Professor James and Professor Bhaskar for the invitation at this very interesting season of school. And so I'm very glad to participate. And I would like just to make a comment now. For those of you that are interested to the technical committee, I am honored to be president of. Since this year, actually, the name of the committee and also the focus research area of the committee has slightly changed. In fact, memristors are now part of the name. There is a slight update. Now it's called Cellular Nonlinear Nanoscale Neural Networks and Memristor Array Computing. So there is the word memristor has been officially now inserted. So if you're interested, you can look on the IEEE CAS website for more details. And for those of you that are interested, they can contact me and we can propose the membership at the next meeting in next year at ISCAS. So thank you, and we can start the presentation now. So this briefly reviews some part of the edge of chaos theory. Of course, I had to summarize a lot, and then I explained how we are applying Professor Chua's theory to investigate complex phenomena in circuits that are currently fabricated at TU Dresden, particularly at the NAMLab company. It's a nanomaterial laboratory company. Director is Professor Mikolajczyk, and so we are actually developing memristor circuits and then studying complex phenomena for unconventional computing, for computing more efficiently than what is currently possible in CMOS technology, leveraging the locally active behavior of some memristors based on niobium dioxide. So we want to apply Leon's Chua's theory to real world circuits to improve, to foster progress to state-of-the-art CMOS circuits. So let's start this talk. So we all know that CMOS technology is approaching atomic scale, and therefore the Moore's law is approaching an inevitable end in the years to come. And so the question is, how can we foster progress in integrated circuit design despite further shrinking in transistor dimensions will no longer be possible? So one of the most interesting, most promising technologies, nanotechnologies, that can allow this barrier to be overcome are the memristors. And so these are essentially, as most of you know, they are state-dependent resistances. So basically you can describe them with Ohm's law, where however the resistance or conductance is state-dependent. And then, of course, you have a differential equation that governs the evolution of the state. The nice feature of memristor devices is that they allow to implement different functionalities in the same physical medium, such as computing, storing data, sensing data. So really, they can pave the way towards a revolution in electronics. And they enable also the implementation in hardware of unconventional data processing paradigm, such as in-memory computing and spike-based computing. And this can allow to boost the performance of purely CMOS circuits. So this means memristor will be used together with CMOS circuits, typically in crossbar arrays. This is very popular to use memristor in crossbar arrays that are stacked over the metal layers on top of the underlying CMOS. And so in order to complement the functionalities of CMOS circuits and to basically to improve, to overcome the bottlenecks that state-of-the-art circuits currently have. One example is the matrix vector multiplication that has been done efficiently, for example, from the group of Jelmini, in which they showed how simply by using the inherent Ohm's law of memristors, one can accelerate matrix vector multiplication using simple crossbar arrays. And however, we know that memristor devices, as you can see also from this picture above here, are intrinsically very nonlinear. And therefore, we need to recur to nonlinear circuit and system theory in order to develop robust methods to design circuits with memristors in the future. And that's where our role is as theoreticians to basically support circuit design with memristors, using theoretical methods to develop new methodologies to design robust circuits. Now, this is an example of, this is basically current controlled memristor, the most general definition. Of course, we have a state equation and we have Ohm's law, right? And what is the difference between non-volatile and volatile memristors? Okay, so if we turn the power off, so we switch off the power, in this case we turn the current to 0, and then we can monitor the evolution of the state with time, and more importantly, actually, we can monitor the resistance, because the state, of course, evolves in time, and therefore also the resistance. Well, if the resistance converges towards one of a few distinct states, at least two, depending, of course, upon the initial condition, when the power is switched off, then a memristor is said to be non-volatile. So this means that when the power is off, it can store at least two states. Then it's called a non-volatile memory. On the other hand, it is volatile. And in this lecture, we actually are focusing on volatile memristors, the ones that are not used as data storage devices, but in fact are interesting for another reason. And among the class of volatile memristors, those featuring a negative differential resistance region in the current voltage characteristic, the red characteristic shown here, for a particular example of a niobium dioxide device fabricated at Hewlett-Packard, those are very much of interest, because in the region where there is a negative slope for the DC characteristic, they can amplify the small signal. And therefore, they can be used, in fact, as small signal amplifiers. Moreover, stacking a number of memristors of this kind together with a bunch of other linear elements, resistances and capacitances, one can truly develop electronic implementations of neurons. This is in fact called electronic neuron or heuristor. They actually are able to generate action potentials, similarly as our neurons in the brain. And exactly because they have this locally active behavior when they are biased around this region. And Hewlett-Packard also went on using a combination of neuristors to create logic gates based on spike-based computing, and even a cellular automata demonstration. This was done only in software, but anyhow, they demonstrated that it is possible to have universal computation using memristor networks, using devices with such a fundamental capability to amplify the small signal. So they can really emulate the behavior of our neurons, and they can pave the way towards the development of new brain-like machines in the future. So saying that, I think that I made it clear that there is much interest in these devices. They are very nonlinear. We need to study them, and we need to apply methods of nonlinear system theory. So as just we briefly addressed, volatile memristors with these NDR effects can in fact induce complex phenomena, such as a reproduction of the action potential, which is reminiscent of neuronal dynamics. But how does complexity originate, and what are the necessary conditions for a physical system to exhibit complex emergent phenomena? And that's what we want to study in this lecture, this introductory lecture. And let's start with a very simple example in which we will consider linear system, only a linear system, and we'll introduce the theory of edge of chaos using a linear system. So this is called Schua's riddle. Many of you probably have already encountered this in the past. Suppose that we have a black box one port, and it's driven by a voltage source. And we go in the lab and we measure the current flowing into this terminal, and with an initial condition of I0, the current decays exponentially with such an envelope, time constant equal to 1, and that's fine. And now suppose that we add a resistor, a purely passive linear resistor of 4 ohm, and what we would expect, what is common to expect, is that basically from the same initial condition, we end up to the same steady state, possibly slower because we have added dissipation, so probably the time constant should be higher than 1. But what if, in fact, for a particular combination of circuit elements inside the black box, what happens when you add the resistor is actually that the current rises exponentially towards infinity. So we have a divergence of the solution, divergence of solutions inside the circuitry. We haven't yet uncovered what is inside the black box, but it can happen. And in fact, this can happen for a particular choice of elements inside the black box. And inside the black box, so what happens? This is another example of complexity, right? So we already gave an example of complexity, the generation of an action potential in our brain. That's a complex phenomenon. Yet another complex phenomenon, although of course it's an extreme phenomenon, is the divergence of solutions. Okay, the unexpected divergence of solution when we basically immerse a black box one port into a dissipative environment. How may this happen? What is inside the black box? Well, we don't reveal it now. We have to introduce the theory before, but we just say as a hint that there are only 2 basic linear two-terminal circuit elements inside the black box. So actually, in this case, it's a very simple system. We have linear elements inside here, and yet we can have complexity. So actually, but the answer to Schua's riddle, we will give it later on, and it's the essence of the edge of chaos theory. So what is the physical principle, this new physical principle that can explain complexity in physical systems? So various luminaries in the past century have debated with much passion over this concept to try to understand what is the origin of complexity. So from Prigogine to Schrödinger, Turing, and Smale. Now, let us give the answer here. We are lucky we know the answer here, thanks to the pioneering work of Leon Chua in primis. So the local activity and its pair, the edge of chaos, are in fact the missing new principle that explain complexity in physical systems. So local activity principle basically states that complexity and emergent phenomena in open systems, so systems that can exchange energy with the environment, are impossible unless some of the units of the system are blessed with the capability to amplify the infinitesimal, the small signal, what is called, in fact, local activity. Now, according to the luminaries that I just cited earlier on, some of them at least, when they were asked what is the condition necessary for complexity, for example, Schrödinger was stating it is an external supply of energy. You need to supply energy to the system. Ilya Prigogine was talking about the need to have nonlinearity into the system. Okay, these are only partially addressing the problem. In fact, suppose that you have a cellular nonlinear network. Okay, so a three-dimensional lattice of locally coupled dynamical systems. Each system can be, in fact, a circuit. They are locally coupled with resistances, with positive linear resistances. And each cell of the network, suppose that is made of arbitrary interconnection of electrical elements endowed with the two aforementioned conditions for complexity. So we have batteries to supply energy to the cell, and we have also, suppose that we have also nonlinearity, for example, diodes with strictly monotone increasing constitutive relationships in the IV domain, right? And then suppose that you can have any other number of positive resistances, inductances, and capacitances. Well, it can be shown that such a network cannot develop complex behavior. Okay, there is no way that you can observe complex behavior in a network of this kind. Again, I remind that the coupling circuit is made up also of positive linear resistors. Okay, so what is then what is missing? There is some more subtle, some more hidden mechanism that in fact supports the behavior of complex phenomena. And Murray Gell-Mann actually was the one that went closer to the right answer, and he was talking about amplification of fluctuations. Okay, but it was not really clear in which physical variables he was meaning. Okay, so is it position, velocity, pressure? He was talking about the necessity to have some amplification of a small signal, but it was not clear on which type of physical variable. Okay, and in fact, Professor Leon Chua discovered the real variable to be energy. So basically, the local activity principle asserts that the correct physical variable whose amplification is essential for complex phenomena is energy. And now we can go deeper in this definition, especially from a mathematical point of view. First of all, we can say that this definition of local activity is in fact that any system is said to be locally active if and only if it is capable to amplify the small fluctuations in energy. Let us go more mathematical. First of all, local activity may be defined for any physical system. In circuit theory, the definition can also be applicable to any multiport. But for simplicity, and since we are dealing with memristor in this lecture, we will talk about one port, and particularly we will introduce the definition, mathematical definition of local activity for memristor one ports. For more details, I would recommend you this book from Professor Leon Chu and Professor Klaus Mainzer about the local activity principle. There is a lot of maths, but there is also a lot of text describing examples or locally active and systems which support the emergence of complex phenomena from any field, from ecology to economics to of course electronics, where this theory, the mathematical theory, has been established by Professor Chua. So let's define what is let's consider a circuit theory. Okay, so we focus on circuit theory, and particularly we define local passivity and local activity for a memristor one port. So let's suppose that we have a memristor and we bias the device in current form. So we drive a current, capital IQ, into the device. The response in terms of voltage is VQ. So after a transient, of course, we have a dynamics evolution. After a transient, at steady state, the voltage will be BQ. So we can say that the current-controlled memristor is biased at Q, at an operating point. We give the current I, and we have the voltage response. Okay, then we can apply on top of the bias current a small signal, an infinitesimally small signal that, of course, will, as a result, see the emergence of a small signal around also as a voltage across the memristor. And then we have to make a computation. So this is a current controlled memristor. It's locally passive at an operating point Q, VQ IQ, if the small signal net energy that enters the device from time t0 to time t, okay, which can be computed, of course, as the integral of the power, right? we're talking here about local power. Local means infinitesimal, because we have to consider only the small signal perturbation, delta I, and the small signal change in voltage that, as a result, can be appreciated across the terminals. And then you do the integral, of course, from T0 to T. So this is a net energy entering into the device, entering because we are using the associated reference direction for voltage and current. So the current is entering into the plus terminal of the memristor. This is called associated reference direction. Therefore, this is the current that enters into the device. And if this integral, this net energy is positive, it is non-negative, so positive or zero, for all time t, and for each admissible small signal stimulus, delta I, then the memristor, the current control memristor, is said to be locally passive at Q. Of course, we have also then the complementary definition for local activity. So again, let's consider a current control memristor driven by a current source, capital IQ. The voltage appreciated across the terminals of the device, measured across the terminals of the device, is capital VQ. Then we add the small signal perturbation, and as a result, we can measure an offset voltage, again, a very infinitesimally small offset voltage, delta V, across the device. And now we can we can define a current control memristor when it is locally active at the operating point Q, VQ, IQ under consideration. Well, we need to search for one particular small signal stimulus, delta E, such that the local energy, the net local energy entering the device from time t0 to time t bar is negative for at least one finite time instant t bar. So it's enough to find one finite time instant where this integral is negative for just one admissible small signal stimulus. So as you can see, the definition is very rigorous, it's very precise, but it's very difficult to test it, right? It's practically difficult to test it, because before ruling out the possibility that the memristor may ever become locally active at some operating point, one should go through all the possible operating points of the memristor along the DC characteristic and apply all the infinite number of possible stimuli. Okay, drive the device with all possible stimuli. So, and then search, and then look at this integral, compute it for all possible times, because it's enough one instant of time to classify the memristor as locally active if this becomes negative. So of course, this is impossible to test. If I have a device, I want to test whether or not it will ever become locally active, I cannot use the definition, but luckily there exists a powerful theorem called the local activity theorem, which can simplify this investigation. However, it necessitates some preliminary work. We need to find out, for a current-driven memristor, the local input admittance. If it was voltage-driven, we need to find the local input resistance. So this is important to do preliminarily. So let's see what we have to do preliminarily. First of all, we need to derive the DC characteristic of the memristor. How do you find the DC characteristic of the memristor? Well, suppose that for simplicity we consider a generic memristor. Generic memristor means the resistance does not depend on the input, it depends only on the state. Okay, just for simplicity, I just consider a generic memristor model. It's current controlled, so you have a state equation and Ohm's law. And we apply a DC current source through we let current IS flow through the device for one particular value of IS, and then we provide this value into the state equation, and we solve for the zeros of the state evolution function, fx capital IS equal to 0. We find all the possible solutions. Then we insert x1, x2, xn inside Ohm's law, okay? And we find the corresponding voltage values to the current IS. And then we can actually mark the following points, IS V1, IS V2, IS Vn, into the voltage current plane. And then we repeat. So here in this case, for example, for IS equal for the value I equal to IS, we have three possible solutions. This is just an example, of course. And then we go on and we repeat the procedure for all values of IS from minus infinity to plus infinity. And then we can interpolate, okay, all the pairs that current voltage pairs that we derive in all the iterations, and we find the DC characteristic. So this is just an example, of course, and I created it on purpose just to show that, for example, in this case, we have a region with negative differential resistance. So this memristor would be locally active, right? Locally active at this, around this negative sloped region. But we will understand why it's locally active along the negative slope region later on. So this is the first thing that one has to do in order to test if a device is locally active. Now, let's see what happens next. We need to find out what is the small signal impedance for a current-driven memristor. So we have our current-driven memristor, right? And so we apply a current capital IQ, the voltage as a result is capital VQ. Then we have the small signal perturbation, which as a result, as a result we measure a small voltage, a small signal voltage delta V, which is an added offset to the bias voltage. Now, so we have the differential algebraic equation set of our memristor. Okay. What has to be done now? We have to developed the DC characteristic in the previous slide. What are the next steps to find the small signal impedance? So first of all, we have to linearize. Remember the two was riddle. In that case, we didn't have any linearization work to do because it was linear. I told you inside the black box there was a linear circuit, so we didn't have to do this step. We were lucky. So we have to linearize, first of all, the differential algebraic equation set about an operating point Q. For example, I chose this point Q. Then we have to transform the linearized system in the Laplace domain. And finally, the local impedance of the memristor can be computed, of course, by the ratio of the Laplace transform of the small signal response delta V divided by the Laplace transform of the small signal input perturbation delta E. And in general, it will be the ratio of two polynomials in the Laplace variable S, with, of course, the numerator polynomial on the numerator having an order smaller or equal than the order of the denominator. Okay. In order to make you more understand how to work out this procedure, let's consider a first order case. In this case, more general, I consider the state to be an nth order dimensional vector. But what about a simple example, which is actually what happens for our memristor that we fabricate here in Dresden with the niobium dioxide? It is in fact in this form, as we will see later. It's a first order memristor, so the state is only one scalar variable. In particular, it is temperature for our memristor. Anyhow, so how to do these steps? So we have found out already the DC characteristic through the method that I earlier on I discussed. Now we have to linearize the differential algebraic equation set. Of course, the linearization using Taylor series analysis is simple, right? Basically, A, B, C, and D are basically just the elements of the Jacobian matrix evaluated at the operating point. Then we transform the linearized system in the Laplace domain. And then we do simple mathematical manipulation. We derive the Laplace transform of the small signal response in the state. And then we are left only with an equation that has a Laplace transform of the small signal perturbation, delta I, and Laplace transform of the small signal response in voltage. And that's exactly what we need to find out then the ratio between the Laplace transforms of delta V and the Laplace transform of delta E, which is the local impedance, right? The local impedance of the memristor about Q, about the operating point under consideration. And here, of course, we have the gain K, 1, 0, and 1 pole. And it's very interesting because out of this expression, we can actually derive the small signal equivalent circuit of the memristor around any operating point Q. As you can see, OR1 is equal to the gain K, OR2 and L are defined by the poles and zeros. So that's very nice because for each operating point, we have a different values for OR2, L, and OR1. Okay? So simply we need one resistor and then in parallel to the series combination between a resistor and an inductor, and that gives us the small signal equivalent circuit model of the memristor. And that's very interesting, very useful because we can then plug this small signal equivalent circuit inside the larger small signal circuits and make analysis of larger structures, right? So, but however, now that we have derived the local impedance of the memristor, we are in a position to to test whether or not our memristor is locally active at some operating point, because we can use the local activity theorem of Professor Leonchua. What does the local activity theorem state? In fact, it states that there are 4 conditions that if at least one of them is verified, the memristor, the current-driven one port, is locally active at Q. But this implied the preliminary derivation of the local input impedance, which we just addressed in the previous slides. So the first condition is, well, the pole of the local input impedance is lying on the open right half plane. Of course, the system is unstable in that case, and it can be classified as locally active. Then there is condition number 2. The local input impedance has a simple pole on the j omega axis, and the associated residue is either a negative real number or is a complex number. Condition number 3, the local input impedance has a multiple pole on the j omega axis. And condition number 4 is that the real part of the local input impedance of the memristor is negative for at least one real valued frequency. And when I say one real valued frequency, it means it can also be just DC, so omega equal to 0. Okay. And now, if you remember that our memristor has a negative slope, a region of negative slope in the DC characteristic, okay, in that region, of course, the real part of Z is negative. At which frequency? At DC. So you can imagine already that that's why we always say that the memristor is locally active when in a region of the DC characteristic which has negative slope. It is because condition number 4 is verified automatically at DC. Okay. So, but why conditions number 2 and 3 are not so important? They are in fact marginal cases. The most important conditions are 1 and 4. Okay. So these are the conditions. If at least one of them is verified, the memristor is locally active at Q. So it's much simpler to verify, to check for these conditions, right? We have also the expression, the analytical expressions for the poles. So everything becomes very easy. And however, now, what is the definition of edge of chaos? Because we said edge of chaos is actually the pearl of local activities, is where complexity, the seat for complexity actually reside. What is edge of chaos? So we just define now local activity. What about edge of chaos? Well, a one port is said to be on the edge of chaos if it is locally active at some asymptotically stable operating point, Q. So this means that condition number 1, 2, and 3 cannot be verified, but only condition number 4 applies, because the system must be stable. So all the poles are now in the left half of the complex plane. However, condition number 4 is true. So the system is locally active, but stable at the operating point, and so it can be classified as being poised on the edge of chaos. Okay. So now, edge of chaos again is the pearl embedded within the domain of local activity. So all systems are now locally passive. All systems, in this case, particularly, we are interested in memristors, first-order memristors, but in general, systems can be locally passive or locally active. And then, if they are locally active, they can be also blessed by the capability to enter a small region called edge of chaos. And this means that basically the operating point under consideration is stable, but yet local activity, the system is locally active because the real part of the impedance is negative for at least one frequency. And again, as I said earlier on, for our memristor, this frequency is 0. Not necessarily only 0, but at 0 we know that because the DC characteristic has a negative slope region. Okay. So edge of chaos is actually, in fact, an innate characteristic of a dynamical system, and it does not depend on the external environment it interacts with. So actually, the complexity that we were observing in Chua's riddle is not due to the resistor that we added, but it's due to what was inside the black box, as we will see shortly. In fact, if you want to know more about these fascinating topics, as Professor Chua in this message just read kindly by Kitra was suggesting, I would recommend to buy these 4 volumes that have been recently published by Professor Leon Chua. And also, if you want to see a video lecture, we realized this video lecture last year, and so you can access this website. And however, it is necessary to have a password. So if for those of you that are interested, we can interact and provide the password. And I would be happy to write you back about the password, and maybe through Professor James. would be easier, maybe. And so here, basically, there are the fundamentals of the edge of chaos theory, and more details are given, especially on the topic of Hodgkin and Huxley and the generation of neuronal spikes inside our brain. So there is a detailed analysis of the Hodgkin and Huxley circuit in this lecture. It's a 3-hour lecture, so I guess it's nice to divide it in a few parts, in order to enjoy it, because it can be heavy otherwise. It's a 3-hour lecture. Okay, so let's give the solution of Chua's riddle now. At this point, I think we have the tools to understand what was happening there. In fact, you would be surprised to see that the linear circuit that is inside this black box is actually very similar to what we see as a small signal model of our memristors. You remember earlier on we saw our memristor here fabricated with niobium dioxide and NABLAB as a resistor in parallel with a series combination between a resistor and an inductor. But in that case, the element change with the operating point, right? Because at each operating point, the element changes. Here it's very simple. We don't have any nonlinear device. It's just these two simple elements. And why is it on the edge of chaos? Why this system is on the edge of chaos? Actually, this is a voltage control system, right? So we need to find the admittance, right? Because it's voltage control. If you pass through the Laplace domain, it's very simple to find what is the admittance, right? It's 1 over resistor plus S times the inductor, right? And if you see here, if you do the complex plane, you see that there is a pole on the left half plane. So it's stable. The system is stable, right? That's why we have the current converges to a stable state. But if you look at the, if you replace S with j omega, so in the j omega domain, and then you calculate the real part of the admittance, you observe that it's negative, actually not only for one finite frequency, for all frequencies. Actually, it's always negative, right? Strictly negative. And therefore, this means that condition number 4, you remember, for the 4 necessary condition for local activity is true. So the other 3 are not verified, only condition number 4. And that's why the system is active and stable, right? And therefore, it's on the edge of chaos, right? And it is because it is on the edge of chaos that then later on, when we added the resistor, something complex happens, something unexpected happens. I mean, adding a resistor, everybody would clearly think that nothing would change, right? We were thinking that dissipation can only attenuate, slow down the dynamics even further. However, this is not the case here. We insert a 4 ohm resistor. Let us now consider, this was the admittance of the cell without the resistor. Now we add the resistor, so we need to consider this circuitry inside the red box and calculate the admittance, right? Y dash of S. Well, if you do the calculation, now we have 4 minus 2, so it's 2 minus 2S. And as you can see now, the pole moves to the right half plane, and that's instability, right? Actually, here it's also given the real part of the admittance. It doesn't really matter what the real part of the admittance do here, right? Because condition number 1 from the 4 condition of local activity is immediately verified, right? Because we have a pole on the right half plane, so it's unstable. It's definitely locally active, but not stable. So it's not on the edge of chaos. This is simply unstable, and therefore any unstable system is, of course, locally active. And that's why we have this, and that's why we have a time constant equal to -1, and we have an exponential increase over time up to infinity. I mean, this is a system that can be easily integrated analytically. You remember that at the beginning of the lecture, I was giving you also the formula. Very simple. You can do this mathematical analysis, and you can find you can actually solve the differential equation and find out the real form, the formula for this current. Okay, so this is actually what happens, including the passive and linear resistor in series with the original 1 port. The resulting overall voltage-controlled 1 port within the red box is poised on a locally active yet unstable operating regime. So now we have the tools to understand why complex phenomena can appear in a system poised on the edge of chaos. Okay. Now let us now study more about what happens in our device, in the circuits that are based on our device. Okay, so this is actually a sketch for the niobium dioxide device stack, which is fabricated here at NAMLab in Dresden. So the oxide film, which is mostly responsible for locally active behavior, is the niobium oxide film. Here, this is the top electrode, and here at the bottom electrode. And what happened in the lab when we were measuring the DC characteristic with the methodology? We applied actually the system theoretic methodology to derive the DC characteristic, and so we worked with the experimentalists in the lab. And well, we were first deriving current into the device, okay? So for each value of IQ, we were measuring all possible voltages, right? And then we were changing the current. And of course, waiting for steady state and then measuring the voltages. And then we were interpolating all the possible points that we were measuring. But the nice thing is that when you basically control the device in current, that's what we observed. We observed all the points of the DC characteristic. So all this DC characteristic is stable if you drive the device in current. How can you understand this? Well, if you consider the circuit theoretic simple load line analysis, this is very simple to understand. Okay, so for each value of IQ, I equal to IQ is the load line, right? We don't have any resistances here. So load line is this green line for this value of IQ. As you can see, the green line intersects the characteristic only in one point. So, and this happens for all values of IQ. When you sweep the device, this load line up and down, you only intersect the load line once. So it's actually, it's nice because we have complete stabilization. We could observe the whole DC characteristic. Then we repeated the experiment, but we actually drive the device in voltage. And of course, the DC characteristic is the same, but in voltage, you cannot observe it all in experiments. We could not observe the most interesting part for us, right? The negative differential resistance region could not be observed. I will explain you later the stability. So basically, this point was unstable. We could only observe this one or this one, depending on the initial condition. Okay, I will show you later the stability analysis. But that's what I want to show you is that when you drive the device in voltage, the load line now becomes V equal to capital V, right? Capital VQ. So I should write capital VQ. So this one is the load line. So this vertical line starting from V equal to VQ. And of course, you have 1, 2, 3 possible solutions for the circuit, right? Now we have to discuss what about stability. I tell you already that when we were in the lab, we could measure only this part and this part. So the positive differential resistance region could be observed. But the most interesting ones for us, for computing with small signal memristive amplifiers, which is this red negative slope line, could not be observed. Okay, to understand this, so that's why we called it unstable branch. So first of all, we have to stabilize it, but before stabilizing it, let's understand more deeply, and we use a system theoretic method called dynamic route map to understand why here we could observe all points and everything was stable, but here this part is unstable. In order to do that, first of all, we developed a model. I mean, this was done in 2015. Now we have a more sophisticated model, but since this work was originally done with this model, and this model is very nice actually. Besides, it's not a physics-based model, but it's using the unfolding principle from Professor Leonchua. So it's basically developing the state evolution function and the inductance function using polynomial series expansions. Okay, and it's very nice because it is very robust. I mean, using this model in MATLAB or in SPICE, your simulation are quite robust. It matches the experimental data. Of course, it's not as attractive as the physics-based model because physics-based model is more attractive for all of us, right? But however, it works very nicely to reproduce accurately and in a simple form the device behavior. So this was the way we of course we had to tune the parameters using optimization algorithms. Anyhow, these are parameter settings. So we modeled this as a generic memristor. You see that the inductance depends only on the state. However, the nice thing about this die set is that you, as I told you earlier on, you can drive it also in current, right? The memristor. And it's easily to rewrite these equations also in current control form, right? So you just write V equal to G inverse X times I, right? Instead of V, you just write, the 1 over G times E, right? And then you can write it in the current control form. So you can do the two studies, right? In fact, let's write it in the current control form, right? And let's study what happens under current control. You remember under current control in the lab, we could measure all the DC characteristics, right? How to understand this? Well, we consider the drum, right? What is the drum? The plot of the time derivative of the state versus the state. And so we actually just plot the state evolution function. We give a current any value that we want. And as you can see, you give 0. Of course, this is a volatile device, you see? You give 0, you have only one possible solution, right? Power off, this is the power off plot, right? So you have only one point, only one stable solution. You remember in the drum, you have the arrows pointing from left to right for when x dot is positive and from right to left when x dot is negative, right? And these are the equilibria, right? And for I equal to 0, this is the power of plot, right? You see, but however, even if the current is different from 0, you see, you always end up in one solution, right? Only one solution, and it is stable. You see, the arrows are converging to it, right? So that explains why all the operating points are stable on the DC characteristic for current control. This is not the case, however, when you do voltage control. Voltage control, okay. Again, you use this model now, just to show you. Okay, it's voltage, so you use these equations, right? And you just sweep the voltage, right? And now you see that when you, depending on where you are and the characteristic, you can either have one operating point. So V equal to 0, of course, you have only one operating point. We said that it's the same memristor, so it's volatile. When you increase the voltage to 0.625, you see that you have still one operating point, but this is a point which is on the positive differential resistance region. Unfortunately, when we enter the negative differential resistance region, look at 0.875, we have three equilibria, you remember? And this is stable, the left one is stable, the right is stable, but this is unstable. So exactly this one that we are interested into, the locally active one, it's unstable. And then if you, of course, if you increase it even further, you again have only one of them, but we are again, for 1.04, this operating point is unfortunately in the positive differential resistance region. So for voltage control, we have a problem. We have instability. We observed it in the lab, and we confirmed it with the theory, right? With the model. So how to stabilize? But it's not difficult to stabilize the operating point on the NDR under voltage control. You need to add a resistor in series, a resistor which is of particular value, we will see now. Basically, why? Because now what happens now? When you add a resistor, we were adding a resistor, and when we were increasing the resistor, suddenly we could see the whole DC characteristic in the lab, also under voltage control. And then we had to understand what was going to happen, what was happening, how come that for a reasonably large resistor, we were using 330 ohm. So with 330 ohm, we were able to stabilize the whole NDR. So we could actually do the technique for deriving the DC characteristic, and we could obtain the whole characteristic. Now, what is interesting to observe is that also this one can be predicted by the model. Okay, in this case, of course, V changes, right? It's not anymore Vs. If you have a resistor, you have a voltage divider. So V is equal to Vs divided by 1 plus the inductance time Rs. As you see that the voltage across the memristor becomes a function of the state, right? So it's a nonlinear function of the state. And that explains now we will do the analysis again, using the dynamic route map technique. And we will observe that for particular value of Rs, also in the NDO region, our operating point will become stable. Okay, let's focus on this is the dynamic route map for three values of the resistance, starting from 0 and okay, and also the voltage is the voltage that we chose before, right? We are in the NDR. As you can see, you have one stable operating point, one stable operating point. This is the black curve. Unfortunately, the intermediate one is unstable. Now we increase the resistance. You see the dynamic route map changes. You remember that why it changes? Because V, which is in the state equation, is actually now the voltage divider formula, right? It's not anymore just Vs. Okay, so of course you have to change Vs and Rs in order to go always. We are always going to through the same point. Okay, so you have to change Vs and Rs. But with this value of Rs, unfortunately, still not enough. You see, there are still three equilibria in the red region, and the intermediate one is unstable. But if you increase it even further, look, 330 ohm, as I told you earlier on, now you have only one intersection, and it is stable. Okay. This can be seen with the dynamic route map technique, but it can be seen also with load line approach. So this is the DC characteristic in green. You remember that if you apply only the voltage without resistance, you have the load line is simply the vertical line, right? And as you can see, we have three possible operating points: one QR, one Q, and one QL, right? Again, Q in the middle is unstable. Now let's consider again the red case. In the red case, I said Rs is larger than 0, but it's not enough. And look at this is the DC load line. Of course, this is the formula for the DC load line. As you can see, here you see also an inset. This is an inset of this part, right? To an enlarged view. You see that the slope, still you have three intersections, unfortunately, like in the black case. So you have 1, 2, 3 intersections, and see, and this is still unstable. But if you increase to 330, now you have only one intersection, you see? So the idea is that you have to have a slope of the load line in modulus less than the slope of the characteristic of the DC characteristic at the same operating point under consideration. So if you impose this condition, okay, then you have a stabilization condition for the resistance. And this is you have to choose a resistance large enough, right? It is related to the inverse, the modulus of the inverse of the negative of the negative slope, right, of the DC characteristic of the memristor at the operating point. Okay, so we have now the stabilization condition. We can drive the device also in voltage, but then we have to add a stabilizing resistance in series. Okay, and in many cases, of course, voltage sources can have a series resistance. If it's not enough, you have to make it larger. Okay, you have to add one. Now, let's again give the small signal equivalent circuit for our threshold switch. Okay, so again, we already went through the steps to derive this formula, right? So we explained already how to find the local. We were focusing on the local impedance of a current-controlled memristor. Here we are studying. We are basically showing the local admittance, which is nothing else than the inverse of the local impedance. Okay, so basically this is the formula that can be derived. We know now how to derive the pole and the zero for the admittance. We developed the steps. So this is the, as I showed you earlier on, the small signal model of our memristor device. Of course, here I used the formula for the model that I earlier showed for our niobium dioxide memristor. And here it's a very insightful plot, which for any value of Rs and for any operating point, admissible operating point of the device, these are values that explain why our state is actually a temperature. It's the temperature inside the filament of the memristor. So these are actually in units Kelvin. And as you can see, for zero series resistance, for example, the region. So if we go through the x-axis, the region in blue is the NDO region. The region in pink, in magenta, is the lower and the upper positive differential resistance region. Anyhow, the magenta region is the locally passive domain. So we can actually classify all possible device operating points, operating regimes, under both voltage and current control. So in magenta we have, because actually we can just, how did we derive this formula? Simply by investigating the four conditions for local activity, right, from the local admittance. And so this means basically studying only the location of the poles. So it's very simple. You can also study the pole zero diagram. Here, instead of giving the pole zero diagram, I just give the results. Okay, so just studying the local activity theorem, it's nice because we can actually determine by theory what is the operating domain, the operating regime for the system. It can be locally passive in the magenta region, or it can be locally active and unstable under voltage control, right? Or in the blue region, or locally active and stable under current control. In fact, under current control, the system is on the edge of chaos in the NDO region. Okay, it's interesting because if you drive the device in current, of course, you have to consider the inverse of this formula. So basically, it is the zero that becomes a pole. Okay, and it can be shown that the zero always lies in the negative half of the complex plane, and therefore the system is stable. However, the real part of the admittance can be shown it is negative at some frequency, in particular at DC, as we know, because the DC characteristic has a negative sloped region, and therefore the system is on the edge of chaos. So the interesting thing is that this blue region is the region for local activity, but if you drive the device in current, it's actually the region of edge of chaos. It's locally active and stable. If you drive the device in voltage, it's just locally active and unstable. Okay. If you want to see more details about this analysis, of course, with the zero pole diagrams, and I can refer you to a paper on frontiers in neuroscience that it's a 40-page paper that gives the details, and it's published in this year and in January. So you can look for this paper, or you can ask me. It's about edge of chaos in an AMLab memristor. Now, having done a comprehensive analysis of the memristor, now we have the small signal model of the memristor, and we have basically identified all the possible operating regimes of the memristor under both voltage and current control, and also for all possible resistance in series to the memristor. Well, having done that, now we can actually build our oscillator. Because we have all the tools, we can do a comprehensive investigation of the oscillator, having well in mind how the memristor operates. So that's an invaluable preliminary analysis, which can then support a design which is conscious of all possible operating modes of our memristor. So what we did is that we added simply a capacitor in parallel to the memristor, and this basically it's a memristive equivalent of the so-called Person-Hanson oscillator. It's a relaxation oscillator. These are the state equation of the cells. The current is I, is the current to the memristor, so it evolves as Ohm's law. And of course, we are using the model of the device that I earlier showed. And we can do the same analysis. Actually, we can derive the local input impedance for the small signal equivalent circuit of the cell. Okay, and so we can derive from this port the small signal impedance for the cell. And so we have a local input impedance equivalent circuitry for the cell itself. Okay, so this is nice because now we can actually study when the cell enters the local activity domain, because our idea is actually now to build the network of cells, okay, to couple them resistively, so diffusively, so adding just dissipation into the system, and to observe whether or not this system can observe static and dynamic patterns. Actually, so this is another example of complexity. Okay, you have an homogeneous system made up of identical cells, like a cellular nonlinear networks made up of identical cells. Okay, and they're only locally coupled. Okay, and if the single cell is silent, and in particular is on the edge of chaos, okay, we want to see whether or not by coupling resistively cells that are silent, right? They are stable in some operating point. However, they are operating on an edge of chaos regime. Then suddenly static pattern and dynamic pattern formation can emerge. So this is an example of complexity, okay, that mesmerized many luminaries such as Mail and Turing in the past. And that's what exactly we want to study and what we were able to understand. Firstly, I will show you now, since we don't have so much time, the example of 2 cells and also a ring example of 50 cells. So what you have to do is basically when you have this type of, when you want to do this type of analysis for 2 cells, you have to consider basically each cell and consider the small signal model of each cell. And now we have all the tools because we have the small signal model of the memristor. We can find out the small signal model for the cell. Okay, that's what we did here. Now, another analysis that we did is for the single cell before coupling the cells, is to understand what happens if I have bias. Because now remember, we have a memristor, but we have also another state given by the capacitor voltage, right? So it becomes a second order model. Okay, so we need to study everything in the phase plane, in a 2-dimensional plane, which is spanned by the memristor state and by the voltage across the memristor, which is the same of the voltage across the capacitor, right? So I wrote V, but it's VC, it's the same thing, right? And so what we do now, we can change VS and ORS. And so by that, you remember that at DC, you have basically, you don't have the capacitor. So basically you have a biasing circuitry. So you have VS, ORS, and memristor. So depending on how you choose VS and ORS, you remember the load line, you can bias your device in the positive differential resistance regions or in the negative differential resistance regions. So now we will bias the device in different regions. We will also change the slope of the load line and see what happens when you add the capacitor. Okay. So actually, there are various scenarios of interest. So first of all, here we bias the device, the memristor device here. So remember, this is a null line. Null line means is the locus of, remember we have a 2-dimensional system. The states here are X, the memristor state, and VM or VC, the voltage across the memristor. So these are the 2 states, okay? Null line means is the locus where one of the 2 state variables has the time derivative 0. So here it's where X null line means where the time derivative of the state of the memristor is 0. And VM null line is when the time derivative of the state, of the other state, the voltage across the memristor is 0. Okay? And the intersection between the null line is the operating point of the cell, of the 2-dimensional cell. So here we have one possible operating point. In this case, the memristor, as you can see in the top here, is biased in a locally passive operating point, in particular in an operating point on the positive differential resistance branch, which is the lower one. Okay, there the memristor is locally passive, we know already, and it's biased there. Okay, what happens is that the cell has only one operating point. Is here as you see, all these trajectories are nothing else that solutions of the system, okay, you just integrate numerically the equations for different initial conditions. Whatever is the initial condition, you see, you always end up in this point. So this point is stable. So the cell has a stable operating point. Nothing interesting, right? There is no complex phenomena. And the system, the cell it can be shown that the cell is not locally active either, okay? What happens if now we bias the device now in the other positive differential resistance region, right, of the DC characteristic, but in the upper one, okay? Again, the cell has one operating point. Again, from any initial condition, the trajectory is spiral toward the equilibrium point. Again, the cell is silent there, but it's passive. Okay, here I'm not showing you all the analysis of local passivity and local activity for the cell, but again, we have the small signal admittance that we showed earlier on for the cell. So one can study the two poles, the location of the poles, right? And apply the local activity theorem to understand whether or not the system is stable. But I tell you the result. Here the system is stable and locally passive. Here the system is the oscillator is passive and locally stable here. So nothing of interest, right? Now let us bias the device, the memristor device, in a locally active operating point. So it means in the NDO region, negative differential resistance region, but we choose the slope of the load line in such a way there are 3 intersections. So the slope is not so large, right? And therefore you have 3 intersections. And you remember that in this case, the NDO region, the NDO operating point for the memristor is not stabilized, right? So the resistance is not large enough. So it means that the slope of the load line is still too large as compared to the slope of the memristor DC characteristic in this NDO operating point. So this is not stable. And as you can see, now trajectories can move either to the operating point on the left or to the operating point on the right. Okay. In particular, this on the NDO region is a saddle point, as you can see. So actually nothing of interest here, but the system is nice because the system here, the cell is bistable, right? You see, bistable means it has 2 possible operating points. Here we are talking about bistability for the cell, not for the memristor, be careful. So the memristor has now is biased in the NDO region, right? But it's biased with the resistor, which is not so large, right? You remember the example before. And therefore this the NDO operating point is not stable. However, the system can end up either in Q01 or in Q03. So 2 silent states, but it's bistable. It's nice. Bistability is always attractive, right? And now it happens what is most interesting for our lecture. Now we bias the device again in the same operating point, actually in another one, but with a resistance which is large enough. So we are in the NDO region, NDO, and the resistance is large enough to stabilize the memristor there. Now the dynamics depend on the capacitance. So now by tuning the capacitance, we can observe different behaviors. Okay, so if the capacitance is not large enough, for example, for 2 nanofarad, the cell can be shown the cell is on the edge of chaos. We demonstrated this in the paper, so this is another paper. It's a TICAS1 paper. Actually, this is not yet accepted because it's in the 50th anniversary of Professor Chua's invention, a special issue. It has been submitted, so we are waiting for but all the details about why it is on the edge of chaos are there. As you can see here, the cell is stable here. I mean, all the trajectories move into this point, but it's stable, but it's an interesting stability. Because you remember, what is stable and is on the edge of chaos, it hides, it is excitable, right? It hides complexity. So it can become really complex if something is, when we couple this cell to another cell with a resistor. You remember? When systems are stable but edge of chaos, then this is like a hint for possible complexity. They're in fact said to be highly excitable, right? It's a hidden complexity, right? But can emerge in all its strength, as you can see shortly. If the capacity instead is larger than a certain value, and now it's interesting as well, right? The system becomes locally active and unstable. In fact, the 2 eigenvalues, right? Remember the eigenvalues of typically a second order system like this one can be studied also in terms of eigenvalues, right? From the Jacobian. But the eigenvalues are the same as the poles of the admittance, okay? So you can also study, there is an equivalent, right? Equivalence between eigenvalues. So one can study the classical eigenvalues analysis, or you can use the poles of the admittance that we just derived. They are identical. So the poles and the eigenvalues have the same behavior, they have the same values. As you can see, the eigenvalues, they cross the imaginary axis, right? And so you have oscillatory behavior. So all trajectories now end up in a limit cycle, and this operating point becomes unstable. But now, this is definitely very interesting because here the behavior, this is actually where you want to operate your cell if you want to build an oscillator. So if any of you is interested, all these possible scenarios, if any of you is interested to build the oscillator, the relaxation oscillator, then you have to work on this operating domain regime, right? But it's nice because we have mapped the whole complete system. We can tune parameters wherever we want. We know where we end up. But this is now where we focus for the last part of the slides. We focus on this regime, okay? The system is on the edge of chaos. The capacitance is small enough. Actually, we bias the device in the NDO region, and we choose ORS large enough. 100 ohm is enough. In the experiments, we choose 330, but 100 ohm for theory is enough. And the memristor is stabilized in the NDO region, as I told you earlier on. You can have, depending on the capacitance, you can have two possible behavior. If the capacitance is small enough, you have the system is locally active and stable. This is the dark blue region. It's in the edge of chaos. If the capacitance is large enough, you have the development of oscillations. So light blue, the system is locally active and unstable, and it develops limit cycle oscillations. So here in the light blue area, it is locally active and unstable. It's an oscillator. In fact, it develops oscillations. Below, it's silent, but it's on the edge of chaos. So now we will work below, okay? In particular, we will choose, if you choose one particular value for Vs with this resistance here, you are actually moving on a vertical line that goes through this symbol here. For C less than C hat, this is actually a bifurcation line, right? It's the so-called off bifurcation line, right? The system develops a supercritical off bifurcation when the capacitance is set along these points, and this is actually only the NDO region, domain for the state. If the capacitance is larger than this value, you have oscillations. If the capacitance is smaller, so below the bifurcation, the system is on the edge of chaos. So now we consider two cells like this, right? In the edge of chaos. So two identical cells, we couple them with the resistor, right? Through the capacitance node, and we consider the cells biased below the bifurcation line. Okay, so they are on the edge of chaos. Okay, and there is this famous theorem called edge of chaos theorem, again from the theory of Professor Leonchua, that states that a stable operating point of a given one port may be destabilized by coupling the one port to a passive environment, which is actually what happens also for the Chua's riddle and what happens now in the study that we are doing now, if and only if Q is poised on the edge of chaos. And that's what we have done now. We have two cells, identical. They are poised on the edge of chaos. They are silent and stable there, but they are locally active and stable, and therefore they are on the edge of chaos. Now we can destabilize the solution of the array, simple array composed of two cells of this kind, and coupled with the passive resistor. That's what we do. We take two cells. We did this with our NumLab partners. We took two cells, and this is actually the famous experiment of Smale. So actually, we are now resolving Smale's paradox. What Smale did? Smale considered two cells of higher order than the second order cells that we are considering here. Two cells that were silent. Then he coupled it with a dissipative element, and suddenly he saw that the whole system, that each of the two cells, identical cells, were silent on their own. By coupling them with in a passive environment, the two cells were starting to pulse. Okay, so there was this famous 1974 paper from Smale, which was questioning how is it possible that two cells that are silent, coupling them dissipatively, complexity emerges. Okay, they were developing a dynamic pattern. Okay, the simplest dynamic pattern for two cells. That's what we reproduce here with our NumLab experimentalist partners, and we actually use edge of chaos theorem to resolve this paradox. This is a fourth order system now, right? And more details are provided in the paper, but what I want to show you here is more the simulation results. Each one of the two cells can be simulated. I told you earlier on that we have, these are the parameters, where the capacitance of each cell is below the bifurcation capacitance. So the cell is sitting on a stable operating point. This is a simulation, you see that after some transient, the cell is just in a dead state, right? Now we consider the two cells together, same simulation, but okay, we offset a little bit the initial condition, but after a while, you see, nothing happens if the resistance is large enough, the coupling resistance. Look here, coupling resistance is 50 ohm, okay? For all values of RC larger than 50 ohm, it's the same behavior. So this is called homogeneous solution. Why is it called homogeneous solution? Because we have an homogeneous medium, right? Homogeneous means it's made up of identical cells, Okay, and this is called homogeneous solution. Homogeneous solutions means each cell is reproducing the same dynamic at steady state as when it was uncoupled. Okay. However, the so-called symmetry breaking. Symmetry breaking means we can destabilize the homogeneous solution by reducing the resistance. Look at why it is possible. Not because of the resistance. It's because the cells are on the edge of chaos. So they are hiding some complex behavior. It's hidden. Okay. They are only you think they are silent, but they are not. In fact, look at what happens when we decrease the resistance to 49.7. After some time, the transient, look at what happens. The two cell bifurcates, we see. And so, sorry, this is the previous slide. I'm sorry, this one. So you have static pattern, right? This is called Turing pattern. So actually they go to two different steady states. They are different from the steady state of the uncoupled cell, okay? So this means symmetry breaking. So the homogeneous solution becomes unstable, and an inhomogeneous static solution called Turing pattern develops. Even more interesting, when you decrease it even more, at 28, you have that the static solution becomes dynamic now. So the development of oscillatory solution, again, this is a complex phenomenon, right? Unexpected, because we are just coupling them. We are coupling two silent cells with resistor. But this is exactly what Smale observed in 1974, and other people also in chemistry, in chemical reactions, like, for example, the famous Belousov-Zapotinsky reaction. They observed this type of phenomena. Two silent systems suddenly immersed in a dissipative environment could develop complex and shocking phenomena. And this is all explained using the theory of edge of chaos. In fact, here we don't go through the details here. I didn't, due to the time restriction, I didn't tell you how I did it to measure this. And I want also to acknowledge, of course, my co-operators for this work, which was Ahmet Samil Demirkol, Professor Leon Chua, and Professor Ronald Teslav. So these are my co-authors that I want to gratefully acknowledge. So what we did here is basically, you remember that I told you earlier on, we have developed, these are the two cells, right, coupled with resistance. You remember that earlier on, we developed the small signal impedance for each of the two cells, right? So this is the small signal impedance of cell 1, small signal impedance of cell 2. This is the small signal impedance. You can measure the small signal impedance for the array, okay? So one can consider actually the poles of the array small signal impedance. Studying the poles, you understand when the whole system becomes unstable. And it's very nice, you can find, I didn't reproduce it here, but after some easy calculation, you can determine the resistance value at which the operating point becomes unstable. You remember I told you 49 static pattern, 29 dynamic patterns. And you can exactly understand that why the 49 at 49 ohm. This is all explained in the theory. It's predicted by the theory. At 49 ohm, two eigenvalues, the real part becomes positive.
Alon, we are slightly off with the time.
I will finish.
Yeah,
I will finish.
Yeah.
Thank you very much. I just show you this simulation that is basically reproducing similar, but in a larger scale circuit. So we have many cells. You have 50 cells coupled in a ring structure with passive resistors. As you can see, again, each cell is identical to the other. They are all basically poised on the edge of chaos. Okay, they are silent on their own when they are coupled by resistors. In this particular case, okay, I didn't reproduce the number of the value of the resistor, but as the resistor is decreased, at some point, you develop static patterns. This is static patterns developed in a 50, again, Turing patterns developed in a 50 cell array. So that's very interesting because, you know, pattern formation and static pattern formation. This is actually reproduction of biological phenomena with real membristive circuits, membristive nanodevices, and the theory that actually enables to understand the phenomenon at which value of the resistances bifurcations occur. And so that's very interesting for creating brain-inspired machines in the future. Of course, this is only the first step. There is much work to do, but it's nice also because it gives us a promising future to work on these exciting topics. In conclusion, and thank you again, Professor James, for being patient with me. Edge of chaos may be interpreted as a new physics principle, which extends the second law of thermodynamics to open systems. You know, because second law of thermodynamics, in fact, states that complexity is impossible in closed systems, where entropy can be only monotonically increased with time. So, however, in open systems, entropy can also decrease over time. And in fact, in open systems, complexity is possible, and the edge of chaos theory explains why and what are the conditions. Today we started what are the conditions for a system to develop complexity. The theory of local activity enables, in the future, can enable, it has the promising prospect to enable the development of a systematic and rigorous approach to design bio-inspired circuits with small signal memoristic amplifiers. Why? Because with the local activity theory, we can understand when bifurcations happen. Okay, we can understand under which value of the resistances we have the beginning of emergence of emergent complex phenomena. So this is something that will give us the possibility to make a systematic approach to memoristic design, to have some, to benefit and to support circuit design, so to interact with experimentalists. We need to interact and talk more to them, because I think together with them we can do much better than ourselves alone as theoreticians, and hopefully also they believe the same towards us. So again, applications include the development of brain-like machines, biologically plausible neuromorphic systems. So we have plenty of applications in our hands, and I hope that we can interact each one of you soon in these interesting initiatives from Professor James and Professor Bhaskar. Thank you very much. Hopefully next time we can hopefully meet
in person.
In person if this pandemics will end up soon. Thank you.
So so there is one question, and maybe we can take just one question. Beautiful explanations. Thank you for presenting this way, Professor Ascoli. I was just curious to understand when you said points 2 and 3 are little less important in the conditions for the component being locally active. I presume it's because there are less practical observations of simple and multiple poles. Am I right,
exactly.
or is there something more to it?
It was what I was in fact pointing out, because there are marginal cases in that sense. I mean, in the sense that it is more typically when you analyze a system, your poles are either in the right half plane or in the left half plane, right? And so, in fact, most of the examples, also a lot of examples, Professor Leon Chua in the literature, you can observe, okay, system is unstable, you have poles on the right half plane, okay, it's locally active. But for edge of chaos, you need to be strictly stable, and then have this condition number 4, which is what happens also in our if you analyze the Hodgkin and Huxley circuit, where the real part of the small signal impedance or admittance becomes negative at some frequency. The nice thing about memristors with this C characteristic having ND-OR region is that they are locally active because of condition 4 directly, right? Just you see the DC characteristic, it has negative slope. It means that at DC, the condition number 4 is verified, and therefore, of course, they are locally active. It just remains to see if they are locally active and stable or unstable, which makes the difference, because if they are stable and locally active, they are on edge of chaos.
Wonderful. Thank you for a very nice and detailed presentation.
Thank you, Professor James.
Yeah, and even Srijit has typed something, the person who asked the question. Thank you for the answer and loved the presentation. So,
thank you. If you have any other comment, we can exchange emails in the future.
Yeah. So if you have more comments or questions, please type it in the chat and we'll pass it to Professor Alon, and we'll pick it from there. Thank you very much, Alon, and look forward to meeting you.
For me also, thank you to Professor Bhaskar, and to all that have made this wonderful initiative happen.
So now, yeah, Bhaskar, do you want to say something?
No, I just wanted thanks to Alon, and enjoy the Sunday or whatever is left of it.
Here it's still clear. I mean, I know in India it's late, but here
I'm actually in UK right now, so it's very sunny and nice. But
okay. Nice. No, here in Germany, as you know, we are 1 year after you, but the sky is still clear. So
good. Great.
Thank you.
So.